This is slide number 31 and I am your presenter Aslubu Mudassar. Here today we shall describe two methods in order to calculate the convolution. For example, one in space domain, the other one is the Fourier domain. So this is the convolution in space domain. So we are going to evaluate the convolution of object O at xy convolved with the kappa at xy. So these can be computed in the two ways. One method is given in the space domain, which is demonstrated in the figure also. Consider two convolving functions. One consists of delta px and other a function of any shape as shown in A, which in this case is an intensity PSF. So in the figure, in the top row, the left one is actually the kappa, or you can say that it is the intensity point spread function, intensity PSF, convolved with the object on the right, which consists of delta functions. So we are going to convolve kappa, which is in the form of functions on the left with the functions on the right, which is the object O. Now the position PSF. What is the method of calculation? The method of calculation is that position the point spread function, that is PSF, at each position of the delta peaks with the height determined by the height of the delta peak as shown in B. So you see that in the figure B, what we have done is that we have convolved the kappa in the top row to the delta functions on the right hand side of the top row, and we have obtained the function as we have shown in B. Okay. Now sum up the contributions in the overlapped regions shown in B and finally obtain the result as shown in C. So you see that in the figure B, we have placed the point spread function at each position of the delta peaks according to the value of the, or according to the height of the delta peaks, and we have shown the result in B. You see that in the B there are some regions which are overlapped, and we are summing up those regions, and then finally we obtain the signal in C. So actually C is actually the convolution of the two objects, that is one object O, which is on the right hand side of the figure in A, and the kappa, which is on the left hand side in figure A. So we have convolved them and we have obtained the final result, which is shown in figure C. Convolution means injecting. Now concentrate very carefully, that convolution means injecting one function with its reference position to each point of the other function and sum up the contribution in the overlapped regions to obtain the final result. Here the reference position means, for example, in the above example, the reference position means is actually the center of the kappa function, which is in the first row in figure A on the left hand side. This is kappa, and its reference position is the center position of this peak in kappa. So we shall place kappa with its central position at each delta functions, and then we shall obtain B, and finally we shall sum up the contributions in the overlapped region in B, and we shall come out with the result in C. Now what is its relevance to the optical system? Point spread function is the response of an optical system to a point source placed at the input plane. That is the point spread function, that is the PSF, is an image of a point source on the object. So if we have an object, and if you have an object in the form of a point source, and you image that object through an optical system, then you obtain an image which we refer to as the point spread function, or the PSF. Now if an object contains only one single point, for example, which is the delta point source, then the image point will also be a single point as demonstrated in this figure. That is, the single image point is equal to single object point convolved with point spread function. In a real situation, an object contains many points, that is many delta points sources. That is, or in other words, you can say that an object is composed of or consisting of many delta functions of varying intensities, then the image will be the sum of the contributions of all of the system responses to all the point sources. So object, we are considering that object consists of many points. We shall evaluate the response of each point through the system, and then we shall sum up those contributions in order to find out the image at the image plane. So simply an image will be equal to the object convolved with the point separate function, or you can say that the point sources contained in the object convolved with the point separate function of the imaging system will give you the image. And image actually the sum of the responses of all the individual point sources. Okay, here the point separate function is the intensity point separate function as stated earlier. Now we want to calculate the convolution. We want to evaluate the convolution using the Fourier quantities. So the first row is actually the absolute value of kappa, that is the absolute value of the Fourier transform of the kappa or the Fourier transform of the point separate function. And kappa, you see that we have shown kappa or the point separate function over here. For example, in the first row on the left hand side, this is actually kappa or the point separate function. So we shall take the Fourier transform of this quantity, and then we take the absolute square of that quantity, because Fourier transform are generally complex quantities. We cannot show the complex quantities graphically. So what we have to do is that we have to take the absolute square of those quantities, and we have shown that one in the first row. So this is the in the first row in A we have shown this is what the Fourier transform of the kappa or the Fourier transform of the point separate function. So this is what we have evaluated. Now in the second step, that is the absolute value of the capital O at fx and fy, the absolute value of that one, which is equal to the Fourier transform of the object at space coordinates x and y. The absolute value of that one, we have shown that one in the part B. So this is the part B. That is you see that here we have these delta functions on the right hand side in the first row, and we have taken its Fourier transform, and we have shown the absolute value of that Fourier transform in part number B. Here this is part number B. So this is actually the absolute value of the Fourier transform of the delta functions shown in the previous example. So we have these two quantities. Now you see that in C, shown in C, what we have shown is that we have multiplied by the Fourier transform of the object with the Fourier transform of the kappa function, and after multiplication we have shown their absolute value, which is shown in part number C over here. So this is in part number C we have shown. What we have done is that we have multiplied the object in A with the object in B, and then we have obtained the result in C. So this is C. Now in the fourth step, what we are going to do is that we are going to evaluate the inverse Fourier transform of the product of capital O at fx, fy with capital K at fx, fy. So we are taking the inverse Fourier transform of the product of these two Fourier transform, and then we are showing the absolute value of these quantities in part D. So here in part D we have. So what we have done is that we have obtained C. You know that we have given the method how to obtain C. Then we have taken the inverse. Then we have taken the inverse Fourier transform of C, and then we have shown the absolute value of that quantity, which is shown in D. And here you see that D is the same result we have obtained using Fourier techniques, Fourier transformations through the Fourier method. And you see that this is in the space domain. This is the convolution in the C, this is the convolution in space domain, and this is the convolution in the Fourier domain. So this is the D in the convolution in the Fourier domain. So convolution, if you carry out convolution in the Fourier domain or you calculate the convolution in the space domain, both will give you the same results. And here we have given that the Fourier quantities are complex quantities and only their magnitudes can be shown. That's why we have shown the absolute square of those quantities in this diagram. That is in this diagram all the quantities we have shown, they are the absolute values of the Fourier transforms. So we can compute the convolution either through the space domain variables or through the Fourier space domain variables, and we have demonstrated that both results will be identical to each other. And so this is the end of slide number 31.